Over the next couple of chapters, we're going to start looking at carbonyl chemistry, the chemistry of carbonyl compounds, and we're going to kick that off in this chapter by looking at some of the more simpler ones, namely aldehydes and ketones. So to jog your memories, a carbonyl group is a carbon double bonded to oxygen. Now, that leaves two more bonds in the carbon, and based on what those two bonds are, you've got the difference between an aldehyde and a ketone. In the case of a ketone, both of those bonds are to some sort of alkyl group, so some carbon-containing group, whereas in the case of an aldehyde, one of those has to be a hydrogen. Okay, so these functional groups are pretty common in a lot of molecules. You've probably already seen quite a few in lab already. So anyway, nomenclature for this again follows a lot of the similar patterns that we've seen in other organic compounds. Of course, we're going to look at our parent chain, our longest continuous chain of carbons containing the functional group, in this case the carbonyl. And so in the case of an aldehyde, we end our name with al for aldehyde. So you take your the alkane name and replace the e with an al. Okay. So for example, here we have butane, which with 4 carbons. You drop the e and it becomes butanal. All right. A quick note here: you've probably noticed that these in the case of an aldehyde, the carbonyl is terminal. This hydrogen can't really bond to anything else, so this carbonyl has to be at the end of the molecule here. All right. So that's going to be very important when it comes to assigning locants. That carbonyl is automatically in the number 1 position. Okay. So keep that in mind when numbering your carbons, because if this molecule has a carbonyl taking priority over any other lower level groups, that carbonyl has to be at the number 1 position. Okay, and you number your substituents accordingly. All right. This one's probably a little bit of a tougher problem because we've got multiple functional groups. You can see that in addition to the aldehyde here, we have an alkene. We also have an alcohol group. So we're going to have this take priority over the others. So again, like when you're naming a molecule like this, take the longest carbon chain containing that functional group, containing that carbonyl, and use that as your root word. So in this case, you want to include this longest carbon chain that includes that alkene, that includes that alcohol group. So this is going to be a propyl substituent on that carbon chain. Okay, so if you've paused this video and come back after taking a stab at this question, you can see here we've got 1, 2, 3, 4, 5, 6, 7 carbons. Okay, so that's going to be a that would be heptanal. Due to the alkene over here, instead of calling this heptanal, like taking that root word heptane, we're going to use the root word heptene. So this is going to be a heptenal. Now, this alcohol group here, we're treating this as a substituent. If this were the main functional group, our name would end with all. Instead, we're going to use hydroxy as the prefix for this functional group. So let's start off with that root name. So we have, like I said, we're going to have heptenal as our root word. Again, we're taking heptene, the long 7 carbon chain alkene here, that's containing our aldehyde, and we're going to change that e at the end to al. Okay, so heptenal is going to be our root word at the end of our name. Heptene. And again, it's like, heptene would be H-E-P-T-E-N-E. We're going to change that last E to al. All right. Now, we don't need to put a locant here for the aldehyde. It's going to be 1, so it's kind of redundant. But that being said, we do need a locant for the alkene over here. So remember, we're starting off from that carbonyl carbon. So it goes 1, 2, 3, 4, 5, 6, 7. So our alkene's at the number 4 position. So it's 4 heptenal. Of course, you could insert that locant in the name. It could be hept 4 enal if you'd like. But I personally prefer putting the numbers in front if I can. Though once we start getting the ketones, you'll see that sometimes it's better to put the number in the middle just for clarity's sake. All right. Anyway, let's name and number our other substituents. So we've taken care of the aldehyde. We've taken care of the alkene. We have a propyl group and an alcohol group, also known as a hydroxyl group, or we use the word hydroxy as a it's prefixed when we put it in here. So hydroxy comes before propyl. So this would be 7-hydroxy. And our propyl group's in the number 3 position, so that's 3-propyl, 4-heptenal. Again, a molecule like this with 3 major functional groups, this is kind of a tougher problem. You wouldn't see something this complicated in a quiz or exam, but this is a nice practice problem to try and get the hang of how to name these aldehydes. Ketones are very similar. Instead of ending with al for aldehyde, we end with one for ketone. All right. So for example, butane here becomes butanone. But now the problem is your carbonyl could have multiple locations, all right? Unlike an aldehyde where that carbonyl has to be terminal, it has to be at the number 1 carbon, because an aldehyde by definition has a hydrogen sticking off of it. In the case of a ketone, it could be anywhere in your carbon chain. Now, in the case of butanone, it has to be at this number 2 position. So you can't have it at the number 1 carbon because then it would be butanal. You can't have it at number 3 carbon because it's just butan. That's just the number 2 carbon going from the opposite direction. So butanone actually doesn't need a locant to say where that double bond is. But once you get to 5 or more carbons, you're going to have to start putting in a locant for your carbonyl. It's very similar to what we do for alkenes and alkynes. So, for example, here we have our 7-carbon chain. That's our parent chain, so that would be a heptanone. The carbonyl is at the number 3 carbon, so it becomes 3-heptanone. Though, as I mentioned, you can also insert the locant in the name, just like we've seen before with alkenes and alkynes. So heptan 3-one is also a legitimate name that you could use here. All right. So with that in mind, let's try another problem like this. Again, I have to stress this is way more complicated than anything you'd see on a quiz or exam, so don't panic if this seems like a tough problem. We're doing a tougher problem just to get the hang of this. Over here, we can see that we have 2 carbonyls in our compound. This is going to be a dione, just like you can have a diene, where you have 2 alkene functional groups. All right, so we're going to name that, and just like with a diene, you need to have locants for both of those functional groups. Okay, but again, we're going to take the longest carbon chain that contains those functional groups, so that's going to be here. It looks like in this case, we're going to start numbering from this end, because if we start numbering from this end, we go only 1 carbon before we get to the first ketone group, whereas from here we've got to go 2 carbons down before that happens. So here we're going to start numbering, so that's our number 1 carbon with our hydroxy group, our alcohol group. 2, 3, 4, 5, 6, 7, 8. Okay, so we have an octanone, or more importantly, an octanedione. Or, even more importantly, because of that alkene, it's an octenedione. Alright, so there's a lot of modifications to that name. Again, I want to stress that this is an unusually, crowded problem. So, let's break that down. There's 8 carbons, so we know it's going to be ordinarily that'd be octane, but now because of the alkene, we've got octene. This is a situation where it might make sense to put in the locand in the middle of the name, so we know that the locand applies to the ene part of the name. It applies to the alkene here that's at the number 3 position. So we'll call this oct3ene. All right, now normally you just say one at the end, but since this has 2 carbonyls, it's going to be dione. Okay, so octene dione. Again, you could probably put the numbers in here, or you could put it at the start. I'm going to put it in the middle of the name just for clarity's sake. So oct3ene 2,6 dione. All right. And now let's name and number our other substituents. So we have our hydroxy group again and our propyl group. And so once again, going in alphabetical order, it's going to be 1 hydroxy, 5 propyl, oct3ene 2,6 dione. All right. So we've seen aldehydes and ketones as chemicals in reactions in other chapters, okay, oftentimes as the product of a lot of reactions. So just to jog our memories from those previous chapters, we can make basically we can oxidize alcohols into the corresponding carbonyls. All right, so in the case of a primary alcohol, we could oxidize into an aldehyde. Now, if you use a strong oxidizing agent, it'll go on to the carboxylic acid. So we have to use PCC, that's pyridinium chlorochromate, and that will stop at the aldehyde level. Okay, it won't go on to the carboxylic acid. Okay, in the case of a secondary alcohol, of course, that's how we get a ketone. We've also seen that we can do certain ozonolysis reactions will help us out. In the case of a alkene, if we cleave that with ozone and DMS, we will get the corresponding carbonyl. You have to use an alkene for these. If you use an alkyne, remember you'll get the carboxylic acid, not the ketone or aldehyde. Okay, so please be careful of that. But yeah, so depending on what's on your alkene, you can either make aldehydes. If you've got hydrogens on those alkene carbons, you can make the corresponding aldehydes. Or if you only have alkyl groups, well, now you have ketones here once you do that ozone cleavage. All right. This method here is kind of interesting because you've got to remember, in order to see this, it sometimes helps to realize you're making an enol, and it tautomerizes into the resulting aldehyde or ketone. So here we're starting off with an alkyne. If we do a hydration reaction, we do basically we add water across that double bond, we would make the corresponding enol, and then it will tautomerize into a carbonyl. Now the question is, where does that alcohol group show up? And to answer that question, you've got to think, is this a Markovnikov or anti-Markovnikov addition? Okay, so you can see over here, by using this borane agent, we are doing an anti-Markovnikov addition. So that alcohol group winds up on that terminal carbon, and so when it tautomerizes, you wind up with an aldehyde, right? That oxygen from your alcohol, which winds up becoming your carbonyl of your aldehyde, has to be on that terminal carbon there. Okay, your triple bond used to be over here between these two carbons. Now, if you do a Markovnikov addition, that alcohol group is going to go to the more substituted carbon, that internal carbon, and when it tautomerizes, now that carbonyl carbon has 2 carbons attached to it, and therefore it's going to be a ketone. Okay, so the difference between forming an aldehyde or a ketone when you start off with a terminal alkyne is it a Markovnikov or anti-Markovnikov? And if you have trouble seeing this, I recommend, when in doubt, draw that enol intermediate, right? So look at that alkyne, say, all right, what's this going to look like when I add water across this? I know one carbon's going to get a hydrogen, one carbon's going to get the alcohol group. What does that look like? And then you can go from there. All right, and now in the last chapter, we added one more reaction to our repertoire. So all these reactions have come from earlier chapters from last semester, right? But in the last chapter, we saw Friedel-Crafts acylation. You could think of an acyl group as kind of like a ketone as a substituent, right? If you look, basically your acyl group is this carbonyl with an alkyl group coming off of it. So that's an acyl group. And of course, when you attach a carbon to that, well, now it's a ketone. Okay, so we're going to look at the reactions that ketones undergo, aldehydes and ketones undergo at that carbonyl. Um, and you'll notice a lot of patterns here. You'll notice a lot of similarities here. And it really comes down to why do carbonyls behave the way that they do? All right. All right, so to start off here, you've got to consider that carbonyls are pretty good electrophiles. All right, and there are a few reasons for that. The first one's resonance, right? So you've got that electronegative oxygen pulling that electron density towards it. So these electrons can actually swing up to the oxygen, giving it a formal negative charge, and turning this carbon into a carbocation. Okay. Now, obviously, this neutral resin structure is much more stable than this one, but this is not an insignificant resonance structure. You know, this is going to contribute some partial positive charge, some positive character to that carbonyl carbon. Okay, and that kind of makes it a good site. As an electrophile, it's a good site for a nucleophile to come in and attack it. All right. Now, the other thing that helps here, I kind of mentioned that the oxygen is very electronegative. Again, that like with with our resonance structures, uh, that itself also helps in making our carbon partially positive, right? That oxygen sucking away electron density, and therefore, while the oxygen has a partial negative charge, the carbon has to be partially positive as a result. Okay. Finally, I mentioned that the whole point of having a carbonyl as an electrophile is that it's prone for nucleophilic attack. It helps that carbonyls are flat, right? Those carbons are sp2 hybridized. They're flat, they're trigonal planar, which allows easy access for a nucleophile. There's less steric hindrance for a nucleophile to come in and attack that carbonyl carbon. Okay. So all of those are things to keep in mind when we go on to look at mechanisms for the reactions we're going to see, right? Because a lot of them hinge on the carbonyl acting as an electrophile. Okay, you'll notice that common theme running through a lot of these mechanisms. All right. With that in mind, one thing to keep in mind here, we just talked about sterics. Keep in mind that plays a role in the viability of these molecules as electrophiles as well. So, for example, an aldehyde will be more reactive than a ketone just because that hydrogen doesn't take up a lot of room. There's lots of easy access for your nucleophile coming in. Whereas, depending on the bulkiness of those R groups on on your ketone, that may interfere. Despite your carbon being sp2 hybridized, despite the molecule being flat at the carbonyl, the bulkiness of those groups could interfere with how easily a nucleophile can get to that carbonyl carbon. Okay, so the carbonyl acts as an electrophile. Let's look at how the nucleophile attacks this and examine why it appears that sometimes this reaction doesn't seem to go forward. It might help to think of this process as a reversible one. So on one hand, you have your nucleophile attacking your carbonyl carbon. You can see that when that happens, the electrons from the double bond move up to that oxygen, giving it that negative formal charge. All right, and you can see that the carbon becomes sp3 hybridized, and you have the what was the nucleophile attached to that carbon. Um, but in the reverse reaction, what was your nucleophile now leaves as a leaving group. So you have these electrons swinging back down, reforming that double bond. These electrons going back to your to what is now your leaving group, and there we have, what was our nucleophile again. So that's what it basically comes down to. Is your nucleophile also a good leaving group? When it leaves, is it going to be relatively stable, leaving either as a neutral molecule like water over here, or something that can stabilize that negative charge, the way that that squishy iodide ion is able to. All right, so basically, when you think of this process as a reversible process, where you've got a nucleophilic attack in one direction and a leaving group leaving in the other direction, if your leaving group's a good leaving group, well, then the nucleophilic attack doesn't seem to stick. It doesn't seem to last. So now that being said, if you do have a nucleophile coming in, a strong nucleophile that's not a good leaving group, then that forward reaction seems to be more preferable. All right, so we have our nucleophile coming in. We have those electrons swinging up to that oxygen, as I pointed out earlier, and you get this negatively charged ion. And then you just need to do a proton transfer, and this is converted into an alcohol. All right, and here we have our neutral molecule with what was our carbonyl carbon now being sp3 hybridized with the nucleophile attached to it. Okay, yeah, so notice that this way, this is kind of driven forward here, because the reverse reaction just isn't very likely. This nucleophile, you're not likely to break this bond over here very easily. All right. So that being said, if we have a nucleophile that is weak, how can we encourage that nucleophile to attack? So there are scenarios where water happens to be our nucleophile. Like, how do we encourage that forward reaction to kind of take over and push the reaction forward? To do this, we can make the carbonyl more electrophilic. All right, so we can do this. Usually the most common way to do this is to have an acid or a base present to sort of help catalyze this reaction. Let's see that in the next few slides. Okay, so adding an acid, for example, will protonate your oxygen, give it a partial positive charge, and that really encourages these electrons to swing up to kind of counteract that, to get rid of that positive charge and move it to the carbon, which is less electronegative than the oxygen, obviously. Okay, so let's see that that full mechanism with a weak nucleophile. So you have to start off with a proton transfer. We start off with a proton transfer here. Our oxygen on our carbonyl picks up that proton, and now you have this charged species, and then the nucleophile attacks that. Okay, swinging those electrons up and make the final product. Okay, so it kind of has the same steps as we saw earlier with a stronger nucleophile. It just kind of does them backwards. We do the proton transfer first to make that carbonyl more prone to a nucleophilic attack. Okay. Now, that being said, you've got to be careful about, what your nucleophile is here. If you have a strong nucleophile, doing this in an acidic solution isn't quite necessary, right? You have to consider that strong nucleophiles also tend to be basic. So if you have your nucleophile floating around in an acidic solution, well, your acid and base are going to neutralize each other, all right, and are less likely to react with your ketone or aldehyde, so it kind of defeats the purpose there. Okay, so I mentioned earlier that water is a weak nucleophile. It's great as a leaving group because water is a very stable molecule, which in turn makes it a pretty weak nucleophile. So again, when we want to use water as a nucleophile, it helps to have a an acid to increase the chances of that happening. Right, so if you were to draw out the mechanism, you would probably notice that in that first step of a nucleophilic attack that reverse reaction where the water leaves as a water molecule, that would be more likely than the nucleophilic attack. So we have to start off with an acidic solution. Okay, so here you can see, again, the water really wants to do this reverse reaction and leave as the stable water molecule. All right, so let's see the mechanism as a whole. Here again, we're doing this without an acid or base catalyst. And again, I just want to highlight that that the reverse reaction here is probably going to predominate, right? This is not a very stable intermediate, and water, as I mentioned, is very stable as a molecule. That reverse reaction, kicking out the water as a leaving group, is really going to predominate, and this reaction isn't really going to move forward from here. Okay, so that being said, here are some examples of what it looks like when water does act as a nucleophile. There are some cases where the molecule itself can help sort of ease the strain from that unstable intermediate. You can see here with a ketone where you've got two alkyl groups pushing electron density to that carbon. You're definitely not helping things out, right? And so instead, over here, where we have these electron withdrawing fluorines, that actually does bring some electron density down and sort of enable this. It does kind of drive this towards the product here. That being said, I mentioned earlier, it's probably a good way to actually get a weak nucleophile like water to add on is to really instead use an acid or base catalyst. Now, we've already seen how an acid helps drive this reaction forward, making that carbonyl more likely to react. In the case of a base, if you're using a metal hydroxide as your base, well, that effectively is a much better nucleophile than water is. So in this example here, if we use we have a hydroxide ion floating around. Let's say we have sodium hydroxide or potassium hydroxide. That acts as our nucleophile and attacks that carbonyl carbon. And we make this anion again, which can then be protonated by water. Okay, so we wind up still getting that diol product. We have two OH groups that we'd expect to see with water as a nucleophile. Okay. All right. I mentioned earlier that the reactions that can be catalyzed as an acid. We kind of already saw this mechanism, but just to go over it one more time. Again, notice that we make the carbonyl more prone to an attack by first protonating it, putting that positive formal charge on the oxygen, and therefore making this more reactive. It's more unstable, so that nucleophile it wants to react with water, even though water is a weak nucleophile. And again, that drives this reaction forward. All right, so instead of water, let's look at an alcohol acting as our nucleophile. Now, alcohols, like water, are also relatively weak nucleophiles, so we'll find that it does help to do this under acidic conditions to help catalyze the reaction and drive this forward. But instead of adding alcohol groups to our carbonyl carbon, we wind up having alkoxy groups instead, okay, where the alkyl part of our alkoxy group, of course, comes from our alcohol that we're using. All right. Now, we call this molecule that has two alkoxy groups attached to it an acetal. All right. So basically, we'll go to the mechanism of how this happens. I will also point out that please note that this is an equilibrium. All right, so these reactants and these products exist in an equilibrium with each other. This is a reversible reaction. All right, so here's the full mechanism of how we make an acetal. So you start off again, please note this is acid catalyzed, as I mentioned earlier. So we start off with that proton transfer, making our, that positive formal charge on our oxygen, increasing the potential energy of this intermediate, and therefore making it more reactive. And so it readily reacts with this weak nucleophile, our alcohol. All right, and just like with water, we have this charged intermediate. we can deprotonate that and make a neutral intermediate. Now, this neutral intermediate here is called a hemiacetal. So the way to tell is you've got an alkoxy group from your alcohol, and your carbonyl has been converted into an alcohol. Okay, so you have an OH group and an OR group. Okay, then we basically continue on with the rest of the mechanism, again with a proton transfer to drive this forward. So we start off by destabilizing this by having a proton add on to our alcohol. Now notice that here we have now made essentially a water leaving group, right? So this is very stable when it leaves as a neutral water molecule, and that is actually what happens. We basically have the electrons from this oxygen swing down, and we make this intermediate. Now notice the similarities between this molecule, this charged molecule, and this one over here. Okay, so the process actually just repeats again. You have a second equivalent of alcohol come in, attack that carbonyl carbon. It swings those electrons up to the oxygen, getting rid of that positive formal charge. And now you have this charged intermediate, which you can deprotonate, and there's your acetal. Okay, so hopefully, there's lots of steps here, but please notice the similarities between the first half of this reaction to make the hemiacetal and the second half of this reaction to make the acetal. All right. So the thing to realize here is that when you look at that mechanism, you see all those steps and look at all those reversible steps, you say like, wait, that's a lot of steps. Isn't there a way to sort of simplify this? Can't we just do a substitution reaction or something? And the truth is it doesn't actually happen. We don't, we have to reform that carbonyl essentially because a simple substitution reaction doesn't come in, because keep in mind, this would be an SN2 mechanism, and this is a weak nucleophile. Remember, you need a strong nucleophile for an SN2 mechanism to occur. So this actually does not happen. Okay, so a intermolecular, reaction that we just saw is unlikely there. Okay, so let's see some. We kind of use the generic R group for our alkoxy groups. Let's look at actual reactions here. So, for example, here we have methanal, right, or formaldehyde, as you've probably heard of it, reacting with two equivalents of ethanol, and basically you just add those two ethoxy groups from your ethanol to that carbonyl carbon. Okay, and there's your resulting acetal. Okay, if you want to see the hemiacetal for this, just swap out one of these for an OH group, an alcohol group. Okay, and you have the resulting hemiacetal. Okay, with this reaction here, with formaldehyde, this is very product favored. If we use acetone, this is actually reactant favored, so you don't get a very large yield of the acetal. All right. An interesting thing to see here is if you have a diol as your alcohol, you can actually get that second equivalent of alcohol to attack from your diol, and you make a cyclic acetal. All right. Keep that in mind. That's going to be kind of useful in later synthetic problems. Especially the fact that, remember, all of these mechanisms are reversible. So from a synthetic standpoint, being able to add on a cyclic acetal and then remove it is going to be very useful when it comes to protecting groups. So it's kind of very similar to what we saw in the previous chapter, where we kind of added on a sulfonate group and then took it back off when we wanted to block off a particular site on our benzene ring. It's kind of a similar case here. We can kind of protect a carbonyl and stop it from reacting, and then do our reaction and then remove the cyclic acetal here to go back to forming the carbonyl that we need in our final product. All right, so just to summarize that, here we have that forward reaction where we add on our cyclic acetal. Again, we can then do reactions on the rest of the molecule, and then once we've done that, we can just add water in the presence of an acid, and it'll return us back to our carbonyl, right? Back to our ketone. Yeah, so basically here we have a ketone functional group and an ester functional group. We'll talk more about esters in a later chapter on carboxylic acid derivatives. But basically, we can kind of reduce that ester down to an alcohol here. And so to do that, though, if we were to reduce this, we would also reduce this to an alcohol, right? To whatever strong reducing agent we're using. So basically, we first need to protect this ketone before we, attack that ester. Okay, so that's actually what happens. So we in the first step we will use our diol here, ethane diol, in the presence of an acid to change this into a cyclic acetal. Then we'll use lithium aluminum hydride, which is a reducing agent that will reduce this ester down to the corresponding alcohol. And then we can use an acid and water to convert that acetal back into the ketone. Okay. All right, so here's another example of that. So feel free to pause this video and fill in the reagents and intermediates. Okay, and hopefully if you've rejoined us, and if you're having trouble seeing it, please know that here we have an ester group. So as we just saw in the previous example, you can use lithium aluminum hydride here to open that up, as you can see here. All right, and note that we have we've returned back to the aldehyde here. So one of the things we're going to do here is draw out your cyclic ester. So I think I've got that in the next slide. There we go. So that's what that cyclic acetal looks like. And then of course we can open that up using lithium aluminum hydride. It looks like they went straight back to that aldehyde, so you've got to include the step where you convert that cyclic acetal back into the aldehyde. So essentially you use water and acid. Listed here is just hydronium. Okay. By the way, these are nucleophilic, and we've got so we've got a diol here, and we've got another carbonyl. So essentially, if you have an acid present, you'll drive this forward into, again, another acetal. So just like an alcohol or water, acts as a nucleophile here, we can also use an amine. All right. Now, instead we have a nitrogen instead of an oxygen that's attacking our carbonyl carbon. That being said, the mechanism is very similar. You'll see a lot of parallels to the formation of our, for our hemiacetal and acetal, except here we have a nitrogen instead of an oxygen. All right. So here we have our amine coming in and attacking that carbonyl carbon. Those electrons, of course, swing up to the oxygen. We can protonate that to and deprotonate the nitrogen, and we make what's basically the equivalent of our hemiacetal. But instead of a hemiacetal, we've got instead of our alkoxy group here, we have a nitrogen attached to our R group, right? So it's an amine group. We call this a carbonylamine, where of course the all part refers to the alcohol on here, and the amine part refers to, well, the amine. Okay, and then just like with a hemiacetal, we can protonate that alcohol group, make it a better leaving group. It leaves. We make this double bond to a nitrogen, which we can then deprotonate, and this is called an imine. All right, so it's kind of like it's basically like a carbonyl, but instead of an oxygen, we have a nitrogen. Okay, so this is kind of like that intermediate we saw with our um, acetal. So back in the acetal formation, you probably remember an intermediate that looked kind of like this, where you then had another equivalent of the alcohol attacking that carbonyl carbon and driving forward to form the acetal. In the case of a primary amine, we have this imine product is more stable and it just kind of stops here. All right. Note that we lost both protons on our original amine, nitrogen. Notice that both those protons are missing here. So we have to lose those protons in subsequent steps here to make this imine product. All right, so it's very important to realize that a primary amine does this. Okay. Just like with our hemiacetal in our other mechanism, it was very important that we deprotonate that oxygen to give the final neutral product. In the same way here, notice that we have positive formal charges on our nitrogens, and it's important to be able to remove those. Okay, so that's with the primary amine. I'll talk about secondary amines, which have one proton that we can remove, and we'll talk about that in a second. Quick note here about this mechanism. You'll probably notice that we used an acid to protonate our oxygen and to deprotonate, the resulting conjugate base would deprotonate, our nitrogen, things like that. Please note that amines are basic, right? They're going to react with acids present. So there's actually an optimal acidic pH to use here. If you get too far, if you start getting too acidic, your rate of reaction actually goes down because you start soaking up your amines as ammonium ions, and they stop reacting nucleophilic. Okay, so that's something to keep in mind, right? That being said, it doesn't help to have too basic a solution because you do need to protonate your carbonylamine to drive the reaction forward to get to that imine final product. Now, in the example we went through just now, we used a primary amine, and I pointed out that we lost both protons on our nitrogen to form the imine final product. Okay, so you can see in that last step, that's where we lost that second proton, and we are left with our neutral imine product. If we had used a secondary amine, now obviously we can get to the carbonylamine step easily enough. Like that only loses that first proton. A secondary amine has a proton it can lose, but when you get to that penultimate step, this is what that intermediate looks like, right? You have two R groups, two alkyl groups on that nitrogen. There's no proton to deprotonate here, right? So how do we get rid of that positive formal charge in the nitrogen? Well, what happens is you actually remove a proton from the from a neighboring carbon, right? So another carbon down, we remove that proton, and we basically form a double bond over here. Now you can't you can't have two double bonds and a single bond to this carbon, right? That would be 5 bonds. So these electrons instead swing up to that nitrogen, and of course that gets rid of that positive formal charge in the process. Okay, we call this an enamine. Okay, just like an enol, we have an alkene, that's the ene part, and a secondary amine over here. Or sorry, actually it's technically a tertiary amine. It's connected to 3 carbons now. So the key takeaway from here is that if you start off with a primary amine and just react that with a aldehyde or ketone with some carbonyl compound, you'll wind up with an imine product, whereas with a secondary amine you wind up with an enamine. All right, so may be wary of that distinction when you're looking at synthesis problems. Now, instead of using a primary amine to attack our carbonyl, we can use hydrazine and then basically form this corresponding hydrazone. It basically goes through a very, very similar mechanism as we saw previously with a primary amine, right? The only difference is we have an amine on our amine, and that's what we have over here instead of an alkyl group.
Now, this can then be reduced in a base down to the resulting alkane, right? We essentially remove that functional group completely. This leaves very easily as a nitrogen molecule, right? That is driven forward pretty well. And this is an irreversible reaction, of course, that nitrogen's not coming back. So you get a pretty high yield of this product. All right, so this is known as the Wolff-Kishner reduction. All right, and so we start off with our carbonyl, and by reacting with a hydrazine, convert it into a hydrazone, and then reduce it with a base to the corresponding alkane. Okay, so here's the last part of that. So here's that hydrazone, which is kind of like an amine, and here's how reacting with a base will give us the alkane. So effectively, our base comes in, deprotonates that. We get a negative formal charge here. You have these electrons swing down here. It basically, you have this resonance stabilized form. When the electrons are down here on the carbon, you can have that pick up a proton, you protonate that, and then repeat that process again. Deprotonate this nitrogen over here again, so you're removing that second hydrogen, all right? And when these electrons swing over, now you've got a nitrogen-nitrogen triple bond, right, which is basically what you need for a nitrogen molecule. So this bond has to break, of course, because that nitrogen would have too many bonds then, and this whole molecule breaks off as the very stable nitrogen molecule. Okay, you're left again with a carb anion like you did back here, which again you can just protonate and you have the neutral alkane. All right. So again, one of the key features here, even though all these reactions involve a lot of equilibrium steps, a lot of reversible steps, this step over here is not going to be reversible, right? You're not getting that nitrogen gas back, so that helps a lot. Okay, so now you probably noticed I kind of glossed over the first half of that Wolff-Kishner reduction because you've probably started to notice there's a lot of similarities here between how a carbonyl gets attacked by some nucleophile, right? So it helps sometimes to make the carbonyl more prone to a nucleophile attack, to make it more electrophilic. So we protonate it first. We basically have the we kind of avoid that scenario where we have two formal charges by protonating that molecule first, right? So that way we don't wind up with a negative formal charge on the oxygen and a positive formal charge on the oxygen or on our incoming nucleophile once it attaches. Okay. And so then it also helps to have the leaving group protonated, so it leaves really easily. And finally, there are proton transfers there's a proton transfer that makes our product neutral. All right. So generally speaking, a good rule of thumb when you are writing out your mechanism is try to avoid things with too large or too many formal charges. So basically, try and keep things with either neutral or within one formal charge. And more importantly, because you're doing this under acidic conditions, if you do have formal charges, it helps to have them be positive formal charges. Because if you do have any negative formal charges, you've got to keep in mind that you're under acidic conditions, there are protons floating around. That negative formal charge, that atom with a negative formal charge is essentially basic. It's going to try and soak up protons to use up that negative formal charge and give you a product you may not want. So be wary of that. Okay, now let's look at the reverse reaction. We essentially can add water across our acetal and return it back to a carbonyl. Okay, we kind of saw this back when we talked about acetals as protecting groups, right? So essentially, to do that reverse reaction, we use an acid and water, sometimes just written as hydronium, and we'll go back to the original carbonyl. Okay, the mechanism is very, it's basically what we've seen for the formation of an acetal, just in reverse, right? So you have, you protonate one of your alkoxy groups to make it a better leaving group. These electrons swing down, and these electrons swing up to that leaving group. So you lose what was that alkoxy group as an alcohol, and you've got essentially a carbonyl with an R group attached to it. Your new nucleophile comes in, right? So you've got water here acting as a nucleophile, and basically, if you deprotonate that, you've made the hemiacetal. All right. Now, again, you can protonate that alkoxy group and begin this process again, get that to become a better leaving group by being protonated, have these electrons swing down, kick that off. Now you again have this carbonyl that's protonated, of course, and you can just deprotonate that to get back to your original carbonyl compound, whether it's a ketone or aldehyde. All right. So likewise, we've seen that we can take carbonyls, and instead of converting them into acetals, we can convert them into imines and enamines using either a primary or secondary amine. So it makes sense that then we can do the reverse process and hydrolyze them, again under acidic conditions, to return back to a carbonyl and the corresponding primary or secondary amine. Okay, so you can see here if we have an imine, right? Remember, which has a double bond between the nitrogen and our sp2 carbon. We hydrolyze that using an acid and water, and we get the corresponding carbonyl plus a primary amine, right? So whatever this chunk is with the nitrogen, that just has hydrogens attached to it to give the nitrogen 3 bonds. Likewise here, we have an enamine, right? And so we basically cleave that off as a secondary amine, and we convert that into the corresponding carbonyl. Okay, in all of these cases, notice that we've been doing this under acidic conditions. It turns out that hydrolysis isn't very effective when using a base. Okay, with sulfur nucleophiles, we can pretty much do similar reactions as we saw with alcohols. Instead of using an alcohol, if we use a thiol, we'll get a thioacetal instead of an acetal. So basically, you're just, it's the same reaction, just you're swapping out the sulfurs for, the oxygens for sulfurs. And notice we can also do this with a cyclic, with a dithiol to make a cyclic thioacetal. So again, very similar mechanism, very similar reaction. You're just replacing oxygens with sulfurs, though. Okay. So another reaction to consider is instead of the Wolff-Kishner reaction, we can kind of get the same net result. We can go from a carbonyl compound to the corresponding alkane. We're essentially getting rid of the oxygen on our carbonyl. But instead of going via an imine, or instead of going via a hydrazone intermediate, we can instead make a thioacetal, right, in one step, and then use Raney nickel to hydrogenate that, to basically convert that into the corresponding alkane. Okay. All right. By the way, another reaction we've already seen. So back with acyl groups, right? So which, remember, an acyl group is kind of like a ketone, attached to our. We saw with a Friedel-Crafts acylation, we can add an acyl group to our benzene ring. Remember the Clemmensen reduction, where we could then reduce that using amalgamated zinc and hydrochloric acid down into that. Into an alkyl group. Okay, so just to jog your memories, remember we actually used this method to make a primary alkyl substituent on a benzene ring, right? We couldn't do that through Friedel-Crafts alkylation due to basically rearrangements of that carbocation. You would never get a primary carbocation to work there. So the way to do it was through this Clemmensen reduction. But my point here is, of course, that here's yet another method to go from a carbonyl into an sp3 hybridized carbon, okay, into just that alkane, essentially. All right. Let's look at some hydrogen nucleophiles. I kind of alluded to this earlier when we talked about lithium aluminum hydride as a reducing agent. So let's look at lithium aluminum hydride and sodium borohydride. Both of these molecules are good sources of hydride ions. That's hydrogen with a -1 charge. All right, so it's just as a proton is a hydrogen that's missing its valence electron, so it's just the plain proton with no electrons around it. A hydride ion is essentially a hydrogen atom with 2 electrons in its outermost shell. It's got a complete outermost shell. All right, but the fact is, it's that negative formal charge on that hydrogen and its lone pair make it a pretty decent nucleophile, right? So Yeah, so basically you can use lithium aluminum hydride or sodium borohydride, and this will essentially this will reduce your carbonyl down to the corresponding alcohol. All right. So basically, that hydrogen nucleophile, hydride nucleophile, I should say, attacks that carbonyl, swings those electrons in that double bond up to the oxygen, giving a negative formal charge. You're breaking the bond between the aluminum and the hydrogen there. So you could consider, basically, consider these electrons swinging towards that carbonyl, or if you just show the hydride by itself, show that lone pair on that hydrogen going towards that carbonyl. Though again, kind of makes more sense for the hydride to be attached to your aluminium. It's probably more stable than just having a free hydride floating around. Anyway, you then have a negative formal charge on your oxygen, and of course you can just protonate that to make that the corresponding alcohol. Okay, and that's why you have to have an acid in the subsequent step. Okay, now thing to watch out for here. This is pretty basic. Hydrides, of course, are bases in addition to nucleophiles. They will pick up protons and form hydrogen gas. So you have to do this in two subsequent steps. You can't have your lithium aluminum hydride and your weak acid, or dilute acid, I should say, in the same reaction vessel. You've got to do it subsequently. Otherwise, you're just going to waste all of your lithium aluminum hydride and get a whole bunch of hydrogen gas bubbling away. All right, carbon nucleophiles. We've kind of already seen carbon as a nucleophile way back last semester. Actually, towards the end of last semester, when we looked at Grignard reagents, right? The really neat thing about Grignard reagents is that you effectively make a carbanion, and that carbanion is nucleophilic, right? So much like a hydride, you have that carbon nucleophile. So if you look at that carbon that's attached to the magnesium on your Grignard reagent, that carbon has a partial negative, pretty much ionic. So you could say almost a formal negative charge on it. You could consider that these two electrons are pretty much on the carbon, making it a carbanion. And you can draw those electrons going towards your carbonyl carbon, those the electrons of your double bond of your carbonyl swinging back up to the oxygen, and then getting that oxygen protonated. Pretty much the same mechanism we've kind of seen already for a lot of things. Okay, so something to keep in mind for various, whether you have a hydrogen or a carbon nucleophile, it kind of works through a very similar mechanism. Okay, so here's an example. So here we have a isobutyl magnesium bromide, right? That's our Grignard reagent. This carbon over here is what's going to attach to this carbonyl and convert that into the corresponding alcohol. In addition to that carbonyl, in addition to the aldehyde group that we have here, we also have an ester over here. Now we'll go into more detail in reactions that esters and other carboxylic acid derivatives will undergo in the next chapter. But basically, an ester can also undergo a reaction with a Grignard reagent. So this carbanion will also attack this carbonyl. And in fact, you'll actually have two equivalents of attacking. You'll eventually wind up breaking this bond to this oxygen in our ester group, and so you wind up with negative formal charges on this oxygen, and this oxygen. And then, of course, like we just saw with our hydride examples, in the subsequent step, we need to add a dilute acid to protonate those oxygens to give us corresponding alcohol groups. All right, so actually you wind up with three equivalents of this carbanion. One of them will attach to this carbonyl, and you'll get an alcohol group here, and then two of them will attach to this carbonyl, and you'll have an alcohol group here and an alcohol group here. Okay, and again, just like with the last example, the hydrides, you can't have this all in one pot. This carbanion, that negative formal charge on that carbon, is going to make it a pretty strong base. It will soak up those protons, and you will waste your Grignard reagent as basically as 2-methylpropane, right? You'll just get the alkane from this, and you'll have wasted your Grignard reagent. Okay. So another example of a nucleophile we can use here, of a carbon-based nucleophile, is a cyanide ion. All right, so with the cyanide ion, again, you have a negative formal charge in a carbon. It's a good nucleophile there. It's pretty stable, resonance stabilized. It can attack that carbonyl carbon, kick those electrons up to that oxygen. That can get protonated, and again, it's again a very similar mechanism. You wind up with that alcohol group and your nucleophile attached to that carbonyl carbon. Okay, so this is called a cyanohydrin, right? You've got a nitrile group or a cyano group, and an alcohol group, right? That's a hydro part here. The problem with this reaction, where you've got to be really careful, is that you're dealing with hydrogen cyanide, essentially. That's highly toxic, of course. So, you know, you want to try and avoid using this reaction if you can, I suppose. Okay, the reason why we're discussing this, even though obviously there are some dangers to doing this reaction, is that from a synthetic standpoint, it is pretty useful, right? Because once you have that nitrile group on there, you can convert it into other useful functional groups. You could reduce it using something like lithium aluminum hydride to the corresponding amine, or you could hydrolyze it into a carboxylic acid group. So just use a acid and heat, and you convert it into the result in the corresponding carboxylic acid. All right. Another really useful reaction that we can do is called the Wittig reaction. All right. So in the Wittig reaction, essentially what you're doing is you are converting your carbonyl into an alkene. All right, now to do this, you've got to use what's called a Wittig reagent, and we'll talk about how to make that and how we control the other half of that alkene. Okay, but basically, it involves using a triphenylphosphine. All right, so this ylide ion that we use as our Wittig reagent is basically, it has one resonance structure where it's got a negative formal charge on the carbon, which is why it's kind of nucleophilic. But this isn't as unstable as it looks. The resonance does stabilize it a little bit by forming a double bond with the phosphorus atom. Okay, so again, we have resonance between these two, and that, so we do have this carbon being relatively nucleophilic, but it's not super unstable. Okay, so that now you're probably saying to yourself, like, wait a minute though, if we have this resonance structure where where we have the formal charges disappear, we've got the right number of bonds to everything, is that okay, right? Like, why don't we just have it stay as this resonance structure with this charged one as a minor contributor, and therefore this is like actually a horrible nucleophile? Well, two reasons. First of all, before I address that, you're probably looking at this and thinking like, wait a minute, I feel like I've got a wrong number of bonds here. You're looking at that phosphorus and you're saying to yourself, wait a minute, that's got 5 bonds to it. Remember, when you're in period 3 and below, you can have more than 4 bonds. You can exceed the octet rule. So atoms like phosphorus and sulfur and so on are capable of forming 5 or 6 bonds. Yeah, that's actually, and they're large enough that you can fit those many bonds around them. Like, that's not a problem from either an electronics or a steric standpoint. But actually, on that note, that's why this resonance structure on the left is a little bit, we see it's not a minor resonance contributor. We actually have a decent contribution from this resonance structure. The difference in size between that carbon and that phosphorus make the overlap of their p orbitals to make that pi bond over here a little less likely. We've kind of seen that before with carbon and sulfur as well. Okay, so there's that poor overlap, so that pi bond isn't as stable as you think it would be. Okay, so we do see a decent contribution from this resonance structure, and that carbon is decently nucleophilic. Okay, so let's look at the mechanism then. So, as you probably guessed, that carbanion is your nucleophile. It attacks that carbonyl carbon. The electrons, instead of swinging up to the oxygen, actually go over to that phosphorus. Okay, you remember you have a positive formal charge on that phosphorus in this resonance structure. So those electrons actually connect to that phosphorus and make this four-membered intermediate. Okay, now of course you probably realize that a four-membered ring isn't particularly stable, so this transition state has a pretty high potential energy. So it quickly reacts, and does basically these electrons swing over here to this phosphorus oxygen bond. So you're breaking that carbon oxygen bond and you're forming a phosphorus oxygen double bond. Okay, and at the same time you're breaking that phosphorus carbon bond and forming a carbon carbon double bond. Okay, so that's what happens here. You form a double bond between the carbons, you form a double bond between the phosphorus and the oxygen. This is a relatively stable molecule that breaks away, driving this reaction forward. And there's your product, your alkene product. Okay. All right, so in order to control the type of alkene you make, you want to start off, let's talk about how we make that ylide to begin with. To make an ylide, you start off with triphenylphosphine, and this is going to be a nucleophile. You can do a nucleophilic substitution with an alkyl halide. All right, so you just have that come in, do an SN2 mechanism, kick off that halogen, or that halide, and you make this corresponding molecule. Now, with the alkyl group on here and with four bonds to that phosphorus is essentially a phosphonium ion. It's got a positive formal charge. So to neutralize this, we can get a base to come along and pluck off that proton. So we use N-butyl lithium, right? And so this lithium, this butyl anion basically plucks off a proton, leaves as you basically get butane and lithium iodide. In case you're wondering where does the lithium go, remember we have iodide floating around. So lithium iodide is our other byproduct, and you make the corresponding ylide. Okay, so depending on what you're using as your alkyl halide, you control that carbanion half of your ylide accordingly. Okay. All right. So, yep. Let's. So here's basically. Depending on what you use, here's an example of something that's not our methyl group for our alkyl halides. So instead of using methyl iodide, here we're using cyclopentyl bromide, right, or bromocyclopentane. By controlling the alkyl halide you use and looking at the carbonyl compound you use, the ketone or the aldehyde, essentially all you're doing is you're taking their carbon skeletons and linking them together, as you can see here, linking them via an alkene, via a carbon-carbon double bond. All right? So again, this is probably a very useful reaction to add to your synthetic toolkit. Just think like, if you realize like, hey, I need to connect this alkene here, I need to have a double bond here, maybe I can take these halves of the carbon skeletons, tack on a carbonyl and a halogen, and realize I could do the Wittig reaction with those halves. Okay, so if you want to see the full mechanism, here's our alkyl halide as the starting point. Remember, we take triphenylphosphine and then deprotonate that to make the corresponding ylide. The ylide does, attacks that the carbonyl of our ketone. You go through that four-membered ring intermediate, that transition state, intermediate, but it's a very unstable intermediate. So it then, you can cleave off that triphenyl phosphide, and you get the corresponding alkene. Okay, now that being said, you may have noticed that we did this in one way, but we could have done this the other way. We could have had the carbonyl on the cyclopentane, and we could have had our alkyl group on our other branched half of this molecule. Okay, so there's actually more than one way to do this Wittig reaction, depending on the pieces that you have in place. Okay, so we could have done this with with our functional groups on the opposite foot, so to speak. All right, another good reaction to look at involving carbonyls is the Baeyer-Williger reaction. That involves inserting an oxygen using a peroxy acid. All right, so here's a ketone. We basically react with our peroxy acid. This oxygen is our nucleophile here. It attacks that carbonyl, kicks those electrons up. Um, when we essentially have a proton transfer, like an intramolecular proton transfer here, where that proton goes to the carbonyl oxygen on our peroxy acid. Okay, and we actually then do an alkyl shift, right? Now, in the case of if this were an aldehyde, this would be a hydride shift. But essentially, you're doing a rearrangement here where that alkyl group shifts over to that oxygen while this carbonyl reforms and while you break this oxygen-oxygen single bond. And you basically have taken that oxygen from your peroxy acid, inserted it between the carbonyl and one of the groups attached to it, and you have your peroxy acid leaving as the more stable carboxylic acid. Okay, but the net effect here is you've taken an oxygen and you've inserted it between the carbonyl and one of the groups attached to it. Okay. All right. So yeah, this again knows the reversible steps here, but that last step, that rearrangement, is pretty much one way. It's it's going to be a little bit. We have this very stable leaving group. We have these very stable products. We have an ester and a carboxylic acid. We're not going to do this reverse reaction to go back to this high energy intermediate, right? So that's why this is pretty much a one-way reaction. Okay, so what where does that oxygen insert into our carbonyl compound, right? If we have an aldehyde or a ketone, what determines where the oxygen goes? Well, it comes down to which group can shift over a little bit more easily. All right, so and it goes in this order. Basically, a hydrogen, it shifts a little bit more easily than then comes a tertiary group, then comes a secondary group, which is tied with a phenyl ring. So either of those is about even. Then comes a primary group, then comes a methyl group shifting over. Okay, so it goes in that order. So if we look at this ketone over here, and let's look at the two substituents attached to it, right? Attached to that carbonyl. We have a methyl group here, and here we have a butyl group, but it's attached to that secondary carbon, right? A sec-butyl group, if you will. So that is a secondary alkyl substituent, right? We've got two alkyl groups attached to that carbon, and so that is higher up on the priority list compared to that methyl group that's attached. So in other words, our oxygen is going to insert over here. Okay, so if you want to look at the full mechanism, that's kind of what happens. So these electrons shift over. So you have this, that oxygen on your peroxy acid doing its nucleophilic attack, kicking those electrons up to the carbonyl oxygen. We, transfer our proton intramolecularly to that carbonyl on our peroxy acid. And now here's the key thing, right? Which set of electrons, this bond or this bond, goes to that oxygen? Well, as I pointed out, it's going to be this group over here. And so we form a bond between this carbon and the oxygen. Okay, and that's what we observe. Here's the oxygen inserted between that carbonyl and looks like they inserted an extra carbon here. This molecule is slightly wrong. This carbon should have been bonded directly here. Yeah, this is an incorrect drawing. But anyway, my point here is that your resulting ester will look like this. Okay, that oxygen is going to be attached to this alkyl group, not inserted here where that methyl group is. Okay, so I've thrown a lot of, even though these reactions have been, there are a lot of similarities between them, we've got lots of options to work with here. And especially a lot of options, if we use carbon-based nucleophiles, we can extend our carbon skeleton pretty well. We're adding a lot of useful things to our carbon, to our synthetic toolkit that I kind of introduced to you in the last semester. Okay, so yeah, so let's go over three of these new techniques. Though one of them isn't really new. We've seen Grignard reactions already from last semester, so this is really kind of a review of that. But basically, we could basically add carbons through a Grignard reagent. We can use a cyanide ion to add on a nitrile group. And again, notice that since that nitrile group has a carbon, we are extending the carbon skeleton that way. Or we can do the Wittig reaction and have our, whatever the carbon-containing half of our ylid, that basically extends the carbon skeleton that way. Okay. Other things we can do is we can kind of break up the connection of carbons. So we've seen that with the Baeyer-Williger reaction, we can insert an oxygen between a carbonyl and an alkyl group attached to it, right? Or a hydrogen in the case of an aldehyde. But basically, we're inserting an oxygen here, and so we're breaking up this carbon skeleton into two chunks here. Okay, and we make the corresponding ester, so we're also changing functional group. Okay, so let's look a little bit at spectroscopy. How do these molecules show up in our various analytical techniques that we've covered earlier in the semester? We've seen that carbonyls show up generally with a pretty strong peak in the double bond region of IR. Remember, your carbonyls are pretty polar, so that's why we see a relatively strong peak for that interaction. Keep in mind that due to the resonance structure, where you have a single bond between the carbon and the oxygen, that slight single bond character does can shift where your signal shows up, especially if you have groups nearby that stabilize that resonance structure. So, for example, here where we have a conjugated pi bond. We basically have resonance structures where we spread out that electron density, and so we have a resonance structure that's stabilized where that single bond character is present, right? We can shift these electrons here, but the bottom line is that single bond between that carbon and oxygen, that resonance structure is a little bit more stable, and as a result, that the stretch that we see for our carbon-oxygen peak is, at a lower set of wave numbers. Okay. Things to look out for as well. Aldehydes do have a carbon-hydrogen stretch. That hydrogen's attached to that carbonyl carbon. It shows up in the 2700 to 2800 range. Though that being said, it might be kind of hard to see. This is a relatively weak peak. You don't see a very strong one. So anyway, that being said, that is something to look out for. With NMR, that carbonyl will shift protons at a neighboring carbon accordingly. We shift them about 1 ppm downfield. Aldehyde protons, on the other hand, are really shifted downfield. They're going to show up like about 9 or 10 ppm, right? So because remember, those aldehyde protons are attached directly to that carbonyl carbon. Okay, so we have a significant influence from that electronegative oxygen, both from like an inductive sense and from resonance effects. Okay, with carbon 13 NMR, that carbonyl carbon is sp2 hybridized. It'll show up in that 200 ppm range. Again, I think we've talked about all this stuff back in those chapters on IR and NMR, but I'm just jogging your memories here. Okay, so with that in mind, let's do a practice problem. So feel free to pause this video and let's see if we can predict roughly where the proton NMR shifts will show up, like roughly what their ppm ranges are, and then talk about their multiplicity, like how they're going to be split by nearby protons, and their integrals, of course. So and then do the same thing for carbon 13. Okay, so if you're back, let's look at the answer here. So for for our proton NMR, basically our vinyl protons show up, at 6. These are going to show up pretty far downfield, right? At about 4.5 to 6.5 ppm, because they're attached to that carbonyl there. Um, Oh, quick thing to notice here, by the way, this is not a benzene ring. So if you accidentally thought that these protons over here would all show up at around, somewhere in that 7 to 8 range, that's not the case. Okay, these are your typical alkyl protons. So again, keep in mind, like, okay, if you got a methylene group here, what does that normally show up? And it's like that would normally show up at, let's say, like 1.2, but remember it's shifted downfield by 1 ppm due to that carbonyl, so it would show up around 2.2 instead. Um, okay, and then with the sp2 carbons, with your carbon 13 NMR, all of the sp2 carbons show up in that 100 to 150 range, and your sp3 hybridized carbons show up in 0 to 50 range. Let's talk about the splitting and stuff, right? I think that's going to be a little bit more distinctive than just where some of your, basically, if we were trying to distinguish these just based on chemical shifts, these will all show up in that, that relatively upfield. I think what's kind of helpful here are the integrals and the corresponding splitting patterns we're going to see. Okay, so let's draw these out and go from there. So we have 2 protons here. We have 2 protons here. We have that final proton here, and then 2 protons here. Okay, so like I said, this one's going to show up relatively downfield, but how's this going to be split? The only thing nearby is going to be these 2 signals here, which are going to be basically anechotopic. You could imagine that this molecule is more or less flat, and there's a mirror plane running through this whole thing. So these 2 are identical signals, which means that this will be split into a triplet. Okay. Likewise, this gets split into a doublet, right? Neither of these have anything nearby enough to help split them any further, right? These are 1, 2, 3, 4 bonds away. Likewise, this is 1, 2, 3, 4 bonds away. So there's nothing nearby enough to split these any further. Okay, so we see a 2 hydrogen doublet. We see a 1 hydrogen triplet. These 2 split each other, so we're going to see triplets for both of these, and they're both 2 hydrogen triplets. Okay, though keep in mind, this one's going to be shifted about 1 ppm further downfield, so around like 2.2 ppm by that carbonyl. This one's probably going to be shifted a little bit downfield due to having that alkene nearby, and that and I guess you do have some inductive effect from this carbonyl, that's getting kind of far away as well. So I would say that probably this one's going to show up a little bit further downfield than this one. Okay, so both of these groups will show up further downfield, and then this 2 hydrogen peak here. But you can distinguish these 2 then by knowing that this will be a triplet and this will be a doublet. Okay, so all of these are going to be unique. Of course, don't forget we'll have a singlet somewhere around that 9 to 10 ppm range for this aldehyde proton as well. Right? Okay, and I believe that's it for this chapter. So, as always, we've seen a lot of synthetic applications in this chapter. We just ended with a few spectroscopy problems, but definitely practice a lot of these syntheses. I recommend having that reaction wheel of all the reactions you've learned. Look at that in your textbook, have that open in front of you, and perhaps either make flashcards of that or use that while studying, and or do these practice problems and start to internalize some of these synthetic options open to you. Okay, all right, so with that in mind, let's go through these practice problems together. Okay, so here we have a molecule that has a ketone and an aldehyde, as well as other functional group or other substituents. Again, don't panic. You're not going to get something this complicated on a quiz or exam. Okay, this one's interesting because now you've got ketone and aldehydes. You've got to think about, one of those is going to have to be be used as a prefix. The other one's going to be used as the suffix, right? I guess you could have an own al, suffix and enter substituents accordingly. It makes sense to end with al since you don't really need a locand for that. That's automatically the number one position. So basically, we have 1, 2, 3, 4, 5, 6, 7 carbons here. So this is going to be a heptanone al. So yeah, if we had only the ketone, it'd be heptanone, but we're going to add an al to the end there. So let's actually number these carbons to just make this a little bit easier. So if that's our number one carbon, 2, 3, 4, 5, 6, 7. So our ketone is at the number 6 position. All right, so this would be heptan, we'll have to insert that 6 there, heptan 6-one al. Okay, it looks like O'Neill, but onal. And then, of course, we have chlorines at the number 3 position. We have, and there's 2 of them, so it's dichloro, 3,3-dichloro. Here we have a cyclohexyl group. Cyclo, that's CY, that's going to come after CH. So our dichloros come first. So it's 3,3-dichloro. 4. Oops, I'm running out of room here. But so 4 cyclohexyl heptone al. Heptan 6-one al, I should say. Yep. All right. So, I left out the stereochemistry here. We have a chiral center. I should have noticed that. That carbon over here has 4 different groups. You don't see the hydrogen here, but that's different from the cyclohexyl group versus this group versus this group. So you do have to use the Kahn-Ingold prelog system to figure out the R or S designation. So in this case, it's an S designation. Since the hydrogen's pointing away from you, this is actually relatively easy to assign priorities to, right? We've got 3 carbons attached to these. This carbon has chlorines attached to it, so that's definitely going to take number 1 priority. Out of these 2, this carbon has 2 carbons attached to it. This carbon has 2 hydrogens and a carbon attached to it. So I should say 2 carbons and a hydrogen that's not shown. But so this definitely takes the next priority. So this is going to go counterclockwise, hence the S designation. All right, let's try making this carbonyl, this aldehyde here, from an alkyne. But then we can also try making it from an alkyl halide without changing the number of carbons. So pause this and think about your different synthetic options to do this. All right, now with your alkyne, remember, to go from an alkyne to some sort of carbonyl, you'll go via an enol intermediate. Okay, so when you're making that enol, ask yourself, do I need a Markovnikov or anti-Markovnikov addition to make this possible? Okay, so pause this video, see if you can figure this out on your own. All right, so if you're back, here are your 2 options. So you probably noticed to get that aldehyde, to get that, when you're making your enol, you want your alcohol on that terminal carbon, right? Now, that's anti-Markovnikov. So you have to use a bulky borane here, like 9-bbn, to do this, and that's basically, in the subsequent step, use sodium hydroxide and hydrogen peroxide. And if you need to jog your memory, go back to last semester in the chapter on addition reactions across alkynes. But basically, that's how you would form this aldehyde. The intermediate here would be an enal, so you'd have a double bond here and a single bond to your OH group, and then that pi bond shifts over, and the hydrogen on your alcohol group shifts over here, and that's how you basically make that aldehyde. Okay, another way to do this, so here's an alkyl halide. You could swap out that halogen, the halide there, for an OH group. So using hydroxide as a strong nucleophile, notice that this is a primary group, so it's prone to SN2 attack. So you have your hydroxide come in, kick off that bromide, you form the corresponding primary alcohol. Well, you can oxidize the primary alcohol to the corresponding aldehyde using pyridinium chlorochromate. Okay, so PCC will oxidize it and stop at the aldehyde. You have to use PCC as your oxidizing agent. If you use chromic acid or potassium permanganate, this would go on to the carboxylic acid, which obviously you don't want. Okay, let's have a look at this reaction here. We're reacting an aldehyde with a diol. Now remember, alcohols will react with carbonyls to make the corresponding acetal. You'll go through a hemiacetal in the process. Yeah, that's basically the product you're going to make here. You're going to make the complete, you're going to make the acetal, but in this case, since both your equivalents of alcohol are in the same molecule, you're going to make a cyclic acetal. Okay, so draw the whole mechanism, showing how this forms the hemiacetal intermediate and then goes on to the acetal. Okay, so here we go. So you protonate. Remember, alcohols aren't great nucleophiles, so it helps to protonate that carbonyl first to make it more electrophilic. One of your alcohol groups attacks that carbonyl, kicks those electrons up, forms the stable alcohol group. You deprotonate that alcohol nucleophile to make this stable hemiacetal. Sorry, not a, yeah, this is your hemiacetal product, right? Here's your alkoxy group, here's your alcohol group. Then, of course, you can protonate the alcohol, make it a better leaving group, kind of reform this carbonyl, though with the rest of your alkyl group attached to it, not a hydrogen as we had here. Of course, we still have this other alcohol group that's nucleophilic that will attack that carbonyl, and you can deprotonate that to make the final cyclic acetal. Okay. Again, I think they've made a mistake in the slides. If I go back, yeah, it looks like there's 2 carbons here. In this mechanism, they've made it 3 carbons. That's a mistake on their part, making the slide. So if you drew this with only 2 carbons here, and so these 2 carbons were connected together, so you had a 5-membered ring instead of a 6-membered ring, that's correct. Okay, this slide is incorrect. They, they inserted an extra carbon here in all of this. Okay, here we have a amine and we have a carbonyl. Now notice that this amine is a secondary amine. We have 2 carbons coming off of it. So remember, a primary amine would form an imine product. We have a secondary amine, so that's going to make an enamine product. And the question tells you that. It tells you you're making an enamine. Go ahead and draw out the mechanism for that. Okay, it looks like they're just going to show you the last step. So much like the previous slide, you have your nitrogen here acting as a nucleophile, attacking that carbonyl and so on. It's going to go through a similar step up until that, until you get to that imine intermediate. But then see how it goes on to forming the corresponding enamine. Okay, so here's the product. So again, you have that intermediate where it looks kind of like an imine, but there's the positive formal charge on the nitrogen. So to get rid of that positive formal charge, we deprotonate the carbon that's adjacent to that, and that swings down here. Those electrons swing to the nitrogen, removing that positive formal charge, giving it only 3 bonds. But we wind up with the alkene that's next to that. All right, here is an alkene we want to make. The question tells us that we are going to use a Wittig reagent to do it. So go ahead and plot out how you might use a Wittig reagent to do this. Keep in mind, of course, that there are, oftentimes there's more than one answer with the Wittig reagent because you've got 2 moving parts here, right? We've got this half of the alkene and this half of the alkene. You need a carbonyl on one and a halogen on the other. Keep in mind, you've got options there. Okay, so here's the reaction. So you could do it in one of 2 ways. You could have either had your halogen on this half and had your carbonyl on this half, or vice versa. Had our carbonyl over here and our halogen on this carbon here. The bottom line is this carbon and this carbon, or this carbon and this carbon, are going to be connected with that double bond. Okay, so that's how you would do that retrosynthetically. Okay, so here's the full mechanism. If we had the halogen on this group, okay, so remember you use triphenylphosphine. It does a SN2 mechanism, kicks off that that halogen as a halide. Using N-butyl lithium as our base, we can deprotonate that, make our ylide reagent. That can then attack our carbonyl half. Kick those electrons up, make that 4-membered transition state, or four-membered intermediate rather, which is very reactive and will immediately break apart into the phosphoxide and the alkene product. All right, let's try this one out. Okay, now here, before you're probably noticing two things going on, or at least hopefully you've noticed two things going on. One, we've extended the carbon skeleton not just with that nitrile group. So that nitrile group is a change in functional group, so I guess that's probably the first thing you probably noticed. But notice that we are also extending the carbon skeleton. We're adding an ethyl group over here. Okay, so there's more than one step to this process. Okay, keep in mind we're starting off with an alkane. That alone should be raise a red flag, because you should be thinking like, wait a minute, alkanes, those are not really reactive. We probably have to do a lot of work here to try and get this to something that will be reactive, where we can turn into a reagent of some sort. Okay, so I won't say anything, but think about how you start off with an alkane. How do we make alkanes reactive? How do we introduce a functional group to an alkane? Okay, so pause this video, think about that, and try this out, and I'll come back with the answer. Okay, so if you've unpaused this video, let's go through the answer here. So of course, when you have an alkane, you pretty much need to introduce a halogen to it through a radical mechanism. So using either NBS or using bromine and light, you're going to put that halogen at that tertiary position. That's the most reactive position there. Okay, now the problem with that is that position is not where you want to add any groups, right? We want to add it to this group here. So it might help to then convert this into an alkene and do an addition reaction to that accordingly. Okay, well, you see there's more than one option. So first of all, it looks like we convert, using a bulky base, we form the alkene, though I guess we could have used pretty much any base, since, there is really, this is a very symmetrical molecule, so that alkene has to form across one of these arms. And then you can cleave that using ozone, right? And so you essentially, convert, you basically get a carbonyl coming off of this, right? So if you're having trouble seeing this, once you add the ozone to this, you're effectively making this intermediate, all right? So that's after this ozone step. So here's a carbonyl. You can then do a Wittig reaction using an ethyl group on your ylid, and you essentially add your ethyl group to that carbon, right? But instead of adding it as just a regular ethyl group, keep in mind you're changing it to the corresponding alkene. So so after this step here, this is what your intermediate looks like, right? So that's that ethyl group here. Okay. Then we can do a anti-Markovnikov hydrogen, hydrohalogenation here, right? So in the next step, we would do an anti-Markovnikov addition, where the bromine is going to attach to this less substituted carbon, right? We're going to add, instead of, if we just added HBr, the bromine would add here, because that would have been the more stable carbocation. But with the peroxides, we go through a radical mechanism, and we put the bromine over here, okay? All right, and then we can do a substitution reaction using cyanide as a nucleophile. It just, just swaps out, and that's where we get that nitrile group in there. Okay. Oh, whoops! I think I had one too few carbons. Right. This is there's our ethyl group. I just added a methyl group here. So that's actually an ethyl group. There we go. That makes more sense. Yeah. So there we go. So that swapped that out, and there's our molecule just turned around. Okay, that being said, there's probably more than one reaction for that. Here's how you could do that. This was actually, I think, the one I would have had in mind. I would have thought of going through a Grignard reagent intermediate. So basically, you can, you start off, introduce that halogen there, you convert it into an alkene, and then you can halogenate that using, an anti-Markovnikov addition. So you start off with your, so you're adding your bromine to that middle carbon, you convert that into the corresponding alkene, and then with HBr and peroxides, you wind up putting that bromine on a terminal position. Okay, if you use just HBr, your bromine would go back to that middle carbon and it would be back the same way as after that first step. So it's kind of, a silly way to, a very cyclic way of doing things and not really productive. Okay, but then you can convert that into a Grignard reagent. Now you've got an alkyl halide, you react that with magnesium and ether, you insert a magnesium here. Now this is a that carbon is going to be nucleophilic, right? It's going to be a carbanion. So you have it attack a carbonyl with an ethyl group on it. Okay? And so you basically take that carbonyl with this ethyl group on it, and you're going to swap out that bromine for, basically a carbon with an ethyl group and an alcohol group, right? That carbonyl changes into an alcohol group. Okay? So that's here you need to use an acid, dilute acid in the next step to protonate that oxygen to make the alcohol group. Now, again, this is a horrible leaving group, so we tosylate it using tosyl chloride and pyridine. So we change this into an OTS group, and then we can do our nucleophilic substitution with cyanide and make the final product. All right, and that's it for. So that's two possible ways to do this. Those are probably the two that make the most sense. Okay, and that's it for this chapter. So, yep, please. Do try out. You notice that this is very synthesis heavy. Definitely do the homework on this. Try out, get the hang of some of the new synthetic methods we've learned. We didn't have a practice problem there with the Bayer-Williger reaction, for example. Definitely try out all of these different synthetic methods. The more you practice it, the better you get at it, and the more internalized it becomes and part of your synthetic toolkit. But I've hopefully impressed upon you that that this is really useful. These carbonyls are really good electrophilic sites. So there are a lot of cool reactions we can do with that. And of course, we're going to continue that in the next couple of chapters, right? And, we're going to start looking at other carbonyl compounds that are derivatives of carboxylic acids. And we'll notice, that not only is the carbonyl an interesting site, for nucleophilic attacks, but we can also do a lot of chemistry one carbon adjacent to that. So over the next couple of chapters, we're going to get into more reactions and more interesting reactions with these carbonyl compounds. But this is a good place to start. And yeah, good luck on your quiz. Let me know if you have any questions.